Good morning and greetings to everyone. Today our group will be presenting our project entitled Vibration Analysis of a Washing Machine Drum using a 2 degree of freedom system 2DOF. Vibration is an important topic in mechanical engineering because almost every machine experiences some form of vibration during operation. If vibration is not properly controlled, it can lead to excessive noise, discomfort, reduced performance, structural damage, and even equipment failure. In this study, we focus on the front-loading washing machine. Although it is a common household appliance, it is actually a good example of a vibration system because it contains rotating meshes, springs, dampers, and external excitation forces. The aim of this presentation is to analyze the vibration characteristic of the washing machine, determine the damping behavior, study the spring arrangement, and evaluate the dynamic response using a 2 degree of freedom vibration model. Slide 2. Engineering applications. Washing machines are widely used in homes, hotels, laundries, and industries. During operation, especially during the spinning cycle, the rotating drum may become unbalanced because the clothes are not evenly distributed. This imbalance generates vibration forces that are transferred throughout the machine structure. The washing machine consists of several major components. These include the rotating drum suspension spring, damping mechanism, and the machine frame. To simplify the analysis, the washing machine is modeled as a 2 degree of freedom system. In this model, the drum represents the first mesh while the frame represents the second mesh. Both meshes can move independently, making the model more realistic than a single degree of freedom system. Understanding vibration in washing machine is important because it helps engineers improve product quality, reduce maintenance costs, enhance user comfort, and increase machine durability. Slide 3. Classification of vibration. The vibration experienced by the washing machine can be classified into several categories. The first category is free vibration. Free vibration occurs when a system is displayed from its equilibrium position and then released without any continuous external force acting on it. For example, if the washing machine drum is pulled slightly and then released, it will oscillate naturally as its own natural frequency. The second category is force vibration. Force vibration occurs when an external force continuously acts on the system. During the spinning process, the uneven distribution of clothes produces an excitation force that continuously acts on the drum. The excitation force is represented by the equation F of t equals F naught multiplied by sine omega t. This means that the force changes sinusoidally with time. The system is also considered a linear vibration system because the restoring force is proportional to displacement. In addition, it is classified as a damped vibration system because energy is continuously dissipated through dampers and friction. Slide 4. Damping characteristic. Damping plays a very important role in controlling vibration. Without damping, the oscillation will continue for a long period of time and may eventually damage the machine. For this analysis, the system parameters are mass equals 25 kg, stiffness equals 18,000 newtons per meter, damping coefficient equals 600 newton second per meter. To determine the damping condition of the system, we first calculate the critical damping coefficient. The formula is C substitute C equals 2 multiplied by the square root of stiffness times mass. After substituting the values, the critical damping coefficient is 1341.64 Newton second per meter. Next, we calculate the damping ratio using zeta equals damping coefficient divided by critical damping coefficient. This gives a value of 0.447. Because the damping ratio is less than 1, the system is classified as an underdamped system. An underdamped system continues to oscillate after being disturbed, but the amplitude gradually decreases until the vibration disappears. This is actually desirable in washing machine because it provided a balance between vibration reduction and smooth machine operation. Slide 5. Spring and elastic elements. The suspension system of the washing machine contains several elastic elements that help support the drum and isolate vibration. The main suspension spring has a stiffness value of 18,000 newtons per meter. This spring provided the restoring force that returns the drum to its equilibrium position after displacement. The rubber mounts have a stiffness value of 12,000 newton per meter. Their purpose is to absorb vibration energy and reduce vibration transmission to the machine frame and the floor. The machine structure itself has a stiffness of 15,000 Newton per meter. A higher stiffness allows the frame to resist deformation and maintain structural stability. Together, these elastic elements form the vibration isolation system of the washing machine. Slide 6. Spring arrangement analysis. In the analysis, the suspension springs are arranged in series. When the springs are connected in series, the equivalent stiffness is lower than the stiffness of any individual spring. The equivalent stiffness is calculated using 1 over k equivalent equals 1 over k1 plus 1 over k2. After substituting the stiffness value, the equivalent stiffness becomes 7,200 newtons per meter. The lower equivalent stiffness provided better vibration isolation because less vibration is transmitted to the machine frame and the surrounding environment. However, there is also a disadvantage since the suspension becomes softer, the drum experiences greater displacement during operation. Therefore, engineers must carefully balance stiffness and vibration isolation when designing the suspension system.
Mass and inertia are important factors that influence vibration behavior. The drum mass is 25 kilograms. The frame mass is 15 kilograms. In general, a large mass results in lower natural frequency. This can help move the operating frequency away from resonance conditions. Next, we calculate the rotational inertia of the drum. The formula used is I equals 1 half multiplied by mass multiplied by radius squared. The drum radius is 0.25 meter. Substituting the value gives a rotational inertia of 0.781 kilogram meter squared. Rotational inertia represents the resistance of the drum to change the rotational motion. A higher inertia improves stability and reduces sudden changes in angular velocity. The washing machine experiences harmonic excitation during the spinning cycle. The excitation force is represented by F of T equals 100 sin 20T. This means the force amplitude is 100 newtons and the excitation frequency is 20 radians per second. When converted to Hertz, the frequency becomes 30.18 Hz. The displacement response of the system is x of t equals 0.006 sine open bracket 20t minus 25 degree close bracket. This indicates a vibration amplitude of 0.006 meter or 6 millimeters. The response also lags behind the excitation force by 25 degrees. This phase lag occurs because of damping within the system. When a vibrating system first existed, The experiences are transient response. The transient response contains the effect of the initial condition and gradually decreases because of damping. After sufficient time, only the steady state response remains. The steady state displacement is given by x of t equals 0.006 sin point bracket 20t minus 25 degree close bracket. The amplitude remains constant at 6 mm and the frequency remains at the same as the excitation frequency. Engineers are usually more interested in the steady state response because it represents the actual operating condition of the machine. This slide shows the complete 2 degree of freedom model. The drum mass represented as M1 is 25 kilograms. The frame mass represented as M2 is 15 kilograms. The stiffness value are K1 equals 18,000 newtons per meter and K2 equals 12,000 newton meters. Damping coefficients are C1 equals 600 Newton second per meter and C2 equals 300 Newton second per meter. Because there are two masses, the system has two natural frequencies and two mode shapes. The first mode usually involves both masses moving together, while the second mode involves the masses moving in opposite direction. Understanding these modes is important for avoiding resonance and improving machine performance. The free body diagram helps us visualize all forces action on the system. The drum displacement is represented by x1 and the frame displacement is represented by x2. Several forces act on the system. The spring force is proportional to displacement and x acts to restore equilibrium. The damping force opposes motion and dissipates energy. The external excitation force originates from the rotating imbalance inside the drum. Using Newton's second law, engineers can derive the equal of motion for the system and predict its vibration behavior under different operating conditions. This free body diagram forms the basis for the calculation and simultaneous performance in the analysis. In conclusion, the project successfully analyzed the vibration behavior of a washing machine using a 2 degree of freedom vibration model. The study showed that the system is underdamped with a damping ratio of 0.447. The suspension spring and damper effectively reduce vibration while maintaining stable operation. The equivalent stiffness of the spring arrangement was calculated to be 7,200 newtons per meter. The harmonic response analysis showed a vibration amplitude of 6 mm and at an excitation frequency of 20 radians per second. Overall, vibration analysis is essential in improving washing machine design because it enhances comfort, reduce noise, minimize structural damage, and increase equipment lifespans. Thank you for listening.